A singly linked list is one of the most fundamental dynamic data structures in computer science, because it provides efficient memory utilization, flexible insertion and deletion, and an intuitive node-based architecture, making it an essential topic in data structures. A singly linked list consists of a sequence of nodes where each node contains two components, data and a pointer, or reference, to the next node in the sequence. Unlike arrays, linked lists do not require contiguous memory allocation. Instead, nodes are scattered across memory, allowing the list to grow or shrink dynamically based on requirements. The basic operations performed on a singly linked list include creating the list, inserting new nodes, searching for specific data values, deleting nodes, and displaying the contents of the list. The creation of a singly linked list begins with allocating memory for the first node, commonly called the head node. Initially, the head pointer is set to null to indicate that the list is empty. When a new node is created, memory is allocated dynamically. Its data field is assigned a value, and its next pointer is set to null because it becomes the last node in the newly formed list. This newly created node is then assigned to the head pointer if the list was initially empty. If nodes are created sequentially, each new node is linked by updating the next pointer of the previous node, thereby forming a chain of nodes that represent the entire list. Insertion is another crucial operation that allows new data to be added to a linked list at different positions, such as at the beginning, at the end, or at a specific position in the middle. Insertion at the beginning is straightforward. A new node is created. Its next pointer is assigned the address of the current head node, and then the head pointer is updated to point to this new node. This makes the new node the first element of the list. Insertion at the end requires traversing the list from the head until the last node, the node whose next pointer is null, is reached. A new node is then created. Its next pointer is set to null, and the next pointer of the last node is updated to point to this new node. Insertion at a specific position involves traversing the list until the node just before the desired position is found. Then a new node is created. Its next pointer is connected to the next pointer of the current node. And finally, the current node's next pointer is updated to point to the new node. These insertion methods allow maximum flexibility in updating the structure of the list without requiring shifting of elements, which is essential in applications where frequent insertions occur. Searching is another important operation used to locate a specific value within the linked list. Since a singly linked list is not index-based, searching requires linear traversal starting from the head node. In a search operation, each node's data field is compared with the target value until a match is found or the end of the list is reached. If the value is found, the location or pointer to that node can be returned. Otherwise, a message indicating that the element does not exist in the list is produced. Searching is therefore an O(n) operation in terms of time complexity because, in the worst case, the algorithm must traverse all n nodes, despite being slower than binary search in arrays. The simplicity of traversal and node-by-node lookup makes searching intuitive and easy to implement. The delete operation is one of the most essential but slightly more complex operations in a singly linked list because it involves manipulating pointers while ensuring the logical connectivity of the remaining list. Deletion can occur at the beginning, at the end, or at a specific intermediate position. Deletion at the beginning involves updating the head pointer to point to the second node in the list, followed by freeing the memory of the original head node. Deletion at the end requires traversing the list to locate the second last node, since the last node does not have a backward pointer. After reaching the second last node, its next pointer is set to null, and the memory of the last node is freed. Deleting a node at a specific position involves locating the node just before the target node, redirecting its next pointer to the next pointer of the node to be deleted, and then freeing the memory of the deleted node. These delete operations ensure efficient modifications of the list structure without extensive memory movement, something that arrays cannot achieve efficiently. Proper deletion also requires careful handling of edge cases, such as deleting the only node in the list, deleting invalid positions, or handling empty lists. Finally, the display operation is used to print or visualize the contents of the linked list. Displaying involves simply starting from the head node and visiting each node one by one until the end of the list is reached. The display function typically prints the value stored in each node, followed by an arrow or symbol that represents the link between nodes, such as data right pointing arrow, and ends with null to mark the end of the list. This sequential traversal makes it easy to track and verify the list structure during program execution or debugging. Displaying ensures that the user or programmer can understand how nodes are connected, what values currently exist, and whether operations such as insertion and deletion were executed correctly. Taken together, the operations of create, insert, search, delete, and display form the core functionality of a singly linked list and demonstrate its flexibility, adaptability, and efficiency in dynamic memory management. The ability to create nodes dynamically, insert them at desired positions, search for values linearly, delete nodes without having to shift elements, and display the entire structure makes the singly linked list one of the most powerful and widely used data structures. These operations highlight why linked lists are superior to arrays when it comes to frequent insertions and deletions, and showcase their usefulness in applications such as memory management, dynamic data storage, graph representations, CPU scheduling, and various real-time systems where efficiency and adaptability play essential roles.